At a certain moment, you want to introduce an FMEA process in your company, but of course, that doesn't always go as smoothly as possible. But luckily, we have a great speaker on that because Tsjerk Hoekstra is going to talk about that. Tsjerk, welcome to the stage.
Yeah, thank you.
Let's give him a warm welcome.
Zit er een pointer op?
Deze.
Right. So now something completely different. You learned, and everyone saw probably tegenlicht on Monday. ASML equipment is being used to fabricate chips. So I've been involved in developing the processes or new processes in the manufacturing and in the design of these chips. So I couldn't resist because I have a room full of failure mode experts here. If anyone recognizes this failure mode, which I came across, I think about 6 months ago. Anyone? No? Any materials experts here? No. Whiskers, yeah, it's getting close. So you saw that there are grains here, so this is a sort of metal. And I'll give you a little bit more information, ask the question again. So we already talked about the dimension a little bit. You see the grain, so it's a nanometer scale here. If we zoom out a little bit, you see here a gold track. It's on silica deposited. And here you see the functionality. It's a coplanar waveguide with a RF signal in the middle and 2 ground plates on the side. Anyone knows what's happening here? Yes?
The idea could be the effect of halogens working in the metal.
It's getting in the right direction. Right in the right direction. Okay, I'll give you the answer because I don't have enough time otherwise at the end. This was really complex. It wasn't known. What happened was, and there's only one paper I found, obscure paper, like ASML was an obscure company. This guy left overnight his silicon wafer with a gold layer in his sputter chamber, and the chamber was heated to prevent the moisture absorption on the sidewalls. And he saw the next day he came back, there was a silicon dioxide being formed on the top of his gold wafer, which he couldn't understand because the temperature was about 100 degrees. So he investigated that and found out that silicon and gold have a mixed phase there at relatively low temperatures. The eutectic temperatures of gold and silicon is 363 degrees, so this is much below what you would expect based on the material properties. So what next happened is I showed you the functionality. This happened in biased MP testing, which is 85 degrees centigrade and 85% relative humidity, and the component is biased as it should be in normal use. So that does tilt the work functions here, and that catalyzes this gold silicon intermixing. And actually what's happening, the silicon is migrating. Actually it's dissolved. We get a liquid here at 85 degrees temperature, a liquid of gold and silicon. And then we have the electric field coming from the electrodes, and the gold is pulled along the field lines towards the side electrodes of the coplanar waveguide. So, what I wanted to tell you here, this is something an FMEA could not predict. They are each in itself, some were known, only this obscure paper, some others is completely new. So the reason I'm sharing this with you, it looks very scientific, is that this is an example of what we call a black swan. And the black swan is an event which we cannot predict, has an extremely low probability, and when it happens, has a huge impact. The terminology was made popular by Nassim Taleb. He wrote a terrible book about that, so I don't advise you to start reading that. You don't learn from it, but you see, it would be very good for a TED talk or so. But the black swan has an interesting tale. There was a Dutch angle on it. It was a common expression in the 16th century for something what was completely impossible. Until a Dutch explorer sailed all the way to Australia, sailed up to a river, and there he saw black swans. He was the first Western guy, of the Northern Hemisphere, to see a black swan. So nowadays, black swan is used for something which is perceived to be impossible, but still happens. And you can, by the way, here's now a statue along that river. So if you're ever in Australia, try to visit that. I will show you a little bit more examples. You get a feeling for black swans. I made very busy slides, which is against all confirmations, but I won't read them out. You can have a look at that. On the top, the timeline when it happened, which sort of coincides with my career. The complexity of the problem here, some characteristics, and here, what does the scientific knowledge do? And really pay attention to the dates here and the dates where this happened. Right. So this was the company I worked before I joined Effect Photonics and Smart Photonics. This is consumer electronics for smartphones. So we told, Tony told you this morning that if you have a gadget, there will be something in there which is made with ASML machines. If you have a Samsung phone or an Apple phone or Motorola, you have a chip of mine in your phone. Right, so here I was developing a fully integrated, monolithically integrated MEMS sensor and CMOS circuitry together, which means technology transfer of the MEMS technology into the CMOS foundries. So I was a resident at Magnachip, UMC and TSMC to do these, to introduce these new technologies. And what we did, this was really crazy, because you would think CMOS technology is very well known, but when we started adding the requirements for the sensor in there, like it's sensing, you have to make contact with the ambient conditions, you have electric fields, you have mechanical properties, which needs to be right for the sensor. That was really Pandora's box. There were so many problems that the design space became very complex here. And that's what you see. And that gave about a 2 to 3 years delay in getting these components onto the market. I won't go into the detail here, but you see this quite a number of different modalities and physics going on, from charge trapping, fringe fields, electrolysis, or again on very low temperatures, metal properties, etc. In the end, we did solve it after 3 years. We came up with a sort of a design which is beautiful to look at. It's called the snowflake design, which dealt with all these different requirements. But again, this was not something anyone could predict that this would happen. So, black swan. So that was about 10 years ago. If we go back 20 years ago, I was at the mid of the telecom boom. We raised with a startup company $168 million. From that, we built 3 production facilities, the very first production facilities in the world for photonic chips, 20 years ago. Built 3 clean rooms, and we ran into a lot of problems because we were the first ones to do this. And the problems had all to do with the decoherence of laser light due to all kinds of reasons. And although these were the design issues in the actual design, issues in the conversion of your GDS file, your mask design file into a real mask, that was a big problem. And also in the deposition technologies of the materials. And all had a, let's see, no pointer, no. All had a problem, yeah. All had a problem, had the same outcome in crosstalk, that there was a background signal which was unwanted. And that made it very, very difficult to deconvolute each of these issues. So these gave 3 to 5 years delay. Okay, going back 30 years in time, I worked with a company called AkzoNobel, probably known here in the Netherlands. And AkzoNobel had lots of polymer chemistry knowledge and wanted to diversify into different markets. So we went into the recordable DVDs, films for displays, and electro-optical polymers for telecommunications. They were especially developed. The telecom wavelength is 1.5 micron, which is about here for very low loss and high non-linearity, which you could use to modulate the light. Only they had one problem. They died very quickly if you started to do live testing, and was completely not understood. And what happened is that we found out that in air there's a very, very millimolar concentrations of triplet oxygen. And this triplet oxygen, if you have very high intensity light of 1.5 micron, you get 2 photon up conversion. You could generate singlet oxygen, and singlet oxygen is very, very reactive with the chromophores, which were the active elements of the polymers. So you see here a little that was even widely publicized. AkzoNobel exhibited very poor photochemical stability. There you go. So that business was killed. So, rightio. So these are 4 examples from my career, and we've seen some of the characteristics for the black swans. But you saw that I sort of improved every decade, so that gave my curve, and start to be able to work with these. So the key characteristics we saw: extremely low probability, but an enormous impact, and we saw the business failure as an example, but huge delays can only be explained in retrospective and cannot be predicted in advance. So I saw some of the questions from the previous talk here is exactly about this. What is it we don't know? And now I can start my talk after this introduction. How to do the risk management in a technology scale up and taking new technology and make that into volume production. So we are Smart Photonics. We have technology was originated from Philips Research and the TU Eindhoven. And in 2020, we put together a strategy to become the global leading foundry of photonic integrated circuits. And we called that lab to fab, because it was dabbling around with all of these technologies. And now we want to become the next TSMC. So pretty ambitious there. So what happens if you scale up from a scientific idea to volume is that the events, low probability events, become more and more pronounced, and you run into them. And that's what we saw in my examples as well. They all happen when you start ramp up volume, statistics kick in, and you start looking at more detail, the validation and verification of your technology. So here's the answer to your question. I anticipated that. Yes, so the method works as the unknown known framework. I didn't come up with that myself. Socrates did that, the ancient Greek philosopher, and several philosophers after them. So it is what do you know? What we know already, and that's the known knowns. Then we have what are the assumptions, and which we select and decide to ignore. These are the known unknowns. Then we have the things where we are biased and unconscious of, and we call that intuition. That's unknown knowns. And then have the stuff we don't know. The surprises, yeah, we don't know. That's the space which is left. But we can do something about it once you realize that this is the case. So the known knowns are predictable. You can use analytics data and other facts to check them. The known unknowns, they should not be ignored. Yeah, we are able to confirm these or reject by measurements or hypothesis. Then we have the unknown knowns, and these we can extrapolate data in a open-minded way, so we can recognize patterns and recognize behavior. Okay, but that leaves us with the unknown unknowns, and these are the complete surprises, as I showed in my short introduction. So here's the answer to. So this is the complete space we have, yeah. So the known knowns are predictable. We stick them. They should be in the project plan. They should not be on your FMEA, because that becomes a long excuse list. Some people recognize that. Then we have the known unknowns and the unknown knowns. And these are the ones we want to catch with the FMEA. And then we are left with what we call the black swans. And the FMEA and the black swans are very intricately connected. And the FMEA plays then also a key role in dealing with the unknown unknowns, as we shall see. So we saw the pyramid here already presented, and even this graph, which is explaining the impact of the FMEAs. So if the FMEA is poor, the known unknowns and the unknown knowns, they slip, and they end up at where you want to launch your product or technology at the very late stage, and there's a high cost in establishing the countermeasures, and definitely a delay and probably failure of your business, what you try to do. A good FMEA brings forward the discovery and the solution of the failure mode. So how does this relate to the black swans? So the black swans, if you have a poor FMEA and you're almost to the end, they all happen at the same time. So you can't tell the known unknowns, the unknown knowns, and the known knowns all, all of them happen at the same time. So you can't deconvolute them, and that's a guaranteed failure. However, if we've done a good FMEA, the black swans event is isolated. So now we can recognize the event and do something about it. In a very late stage, but now you get yourself a chance to solve them. But again, by definition, they appear during ramp up and verification stage towards the end. And always by the very nature of the black swans, they are unknown. So solutions are also not known, but you get a delay in developing the solutions. And we have seen from my examples that you have to measure these delays into years or multiple years. Not a quick thing. But here's the solution for you. And that solution I call fail forward. If you want to remember anything from my talk, remember fail forward. That will help you tremendously in your own jobs. And how do we fail forward? We're going to hunt the black swans. Anyone can see him there? Yeah. It's over there. So it's somewhere outside the realm where we normally look and try to look for our problems. And how can we make them appear? It's by using minesweepers, and I'll show you some examples. And the other one is test to destruction. And test to destruction is really important. That you test up your product, even if it's not the final product, but start to do that as soon as possible. And if you see the onset of a failure mode, you start to study that onset, and that gives you the direction where to look for your black swan. Minesweepers are also very favorite. They are, as soon as possible, incomplete, try to make your product or process like it is the real product. And from that you learn a lot of things which is good and which is not good. And again, that gives you a little direction on where to look for black swans. The key one for your business is to build in resilience in dealing with black swans. I've now told you that they will happen. The unknown unknowns will happen. That's what we know. Yeah, this is not language trickery. This is real. This is real. So no excuse on that after today. Then you use the FMEA to separate and isolate the unknown knowns from the rest. And we've talked about that. Build a problem-solving team. This is really important. Try to recruit the brightest guys or girls. And particularly ones, I think, who have a quirk, because they look differently onto problems. Then you have to build a constant baseline, so don't do all these DOEs and design iterations and so on, because that's exactly the place where black swan wants to hide. And that was already said, my favorite, fail forward and test to destruction. It's all common sense, yeah? You agree? Yes. So why it doesn't happen? Why is it so bloody difficult? First of all is, if you shave off 2 years of the program, but it doesn't, because a failure doesn't happen, you won't be recognized for it, yeah? It's not, then we already discussed how we'll do very quickly is build a proper FMEA, and that takes time and effort. You really need to pay attention to that. Then the third one was also a favorite of management. Yeah, they're much more into what went wrong and get it solved. And having demanding daily reports. In the US, we call this spinning the wheels. That means a lot of smoke and action and noise, but you don't move forward. But anyway, the management will like that very much. Already discussed, problems remain hidden in many design and process iterations. There's a tendency with engineers to do that. They always know something better, but so don't do your toast. And the last one you're also, Jan, put down. Magically, I don't know how, but everyone who's writing a project and the engineers involved, no one believes that they will mistake. It will actually, that project will happen as they've written it down. Yeah, true? Good. Some buzzwords. Agile and concurrent engineering, let's call it common sense. What we need is to build in flexibility while keeping a baseline, so that's really important. So you have to deliver functional devices to test as early as possible, the fail forward. You have to put in your project plan safe fallback positions to limit delay. And you have to create options to move onto a different track, basically creating an escape. It's a bit shown here, so be very clear. These are not DOEs or design iterations, but they are carefully planned configurations which maintain the baseline. And all the project plans I did at Effect and started doing in my earlier career, they all look like that and have these built in. And that's why I was able to bring back 3 to 5 years delay back to 2-3 years delay. And now the first example only took 6 months to resolve. We talked a little bit about that. I'll do this quickly. Is what I've done and my colleagues to evangelize FMEA at Smart, and I'll give you some examples. You can read this slide at your leisure, probably when at the handouts. So first of all, it's really into our business process. We, like many companies, we have a phase gate business process. The one we took inspiration from is from NXP. We are a startup company, so you look at your big brother. And we have a gate in there called the A gate, is when we apply a process onto real wafers. And this A gate very specifically has the FMEA and control plan in there. There's no A gate if that's not being delivered by the team who's developed the process and seeking approval. So that's really, really important. That makes it immediately serious, and also that the business is really serious about that. If you become sloppy in that, yeah, then your engineers will take a piss and they won't do the FMEA. This is very detailed tracked into the A gate, and there's a whole database behind it. And in that database is also the FMEA. That's the addressing also some of the issues you said in the previous talk. So it's trackable, traceable, documented into a database. Then the FMEA, before we go to the A gate, that the FMEA is peer reviewed, has to be signed off with the lead engineers and the senior engineers in that field. Otherwise it doesn't get approved. And it is reviewed by our CCB chairman, and if the CCB chairman is not by his, then delegate that to one of his quality engineers. Again, that makes it really formal, really visible. The FMEAs are really extensive. People come together several times before actually that is completed. And also the point here is make them inclusive of those who are actually doing the work. They know a lot more than your senior engineer. Very important. And I did make the slides before your talk. Yeah, this is, I absolutely love this one. So we take the 5 risks and present that in the CCB. The CCB must have management team members available, otherwise it's postponed. So that's a big signal also to our management to really turn up if they don't want to delay the project, because then we make them guilty and make them pay. And we take the top 5 from the FMEA and we discuss that in detail, and that gives a sample to the management team, to the decision makers, whether or not the FMEA is up to standard. And that makes it much simpler. Before I came, we just did the whole FMEA, which is far too complex. But if you take the top 5, you can get a feel for that. But as I said, the thing I really like is our CCP chairman. When the team presenting, they pass the A gate. He also gives a genuine congratulations to the team for completing the A gate. And I think that is really key, really important for the team. So celebrate when you complete your FMEA. Okay, our friends from Holland Innovative, we've asked to provide training to whole the company. Obviously, we have engineers from all over the world, different systems, but we all want to have them on one page. What does the FMEA mean? What detail needs to go into there? And we want all to line that up. So that's why we run this course within our company. Very, and not generic, very specific, tailored to our business. And that's also important because if you do a generic training, it doesn't have the foothold where to be applied. So I've reviewed and adjusted this course for that purpose specifically. And also a bit mentioned, but it's important, FMEA is not the output, because if that's the output from your business process, an FMEA is not be used in anything. Yeah, no one's going to read that huge Excel sheet. So what it has to have is tangible output, control plans, very important. Maintenance plans, sorry, yeah, you already indicated. Design for X can be anything, which is design for reliability, design for test, design for manufacturing. Design rules are an output of the FMEA. And you need to have tangible owners for whether it's process integration, process engineering, equipment engineering. That's you need to involve all of them. Okay, so when I was making these slides, I invented a new acronym. And the acronym is not in my FMEA. NIMF so hopefully you start using that. So if you have your own NIMF, I think please let Holland Innovative know. They can then include that in their courses. So we saw this huge FMEA in one of the other example, the one you could not read all the letters in. And here's a little bit about it. One of the risks is the non-uniformity over the wafer. Yeah, we manufacture wafers. And we have a brand new tool here installed, super duper latest generation. We developed the processes on it. We run DOE's process improvements and did test wafers, short loops, etc. All the good work. Very uniform edge profile, as you can see, it's a uniform color. So then we run our Minesweeper. So remember, Minesweeper is one of my favorites. And we got this profile. So you see a large non-uniformity in a very distinct pattern. So I started my talk with a question. I'll ask it here towards the end as well. Anyone has an idea what's going on here? You're all experts, failure mode experts. No, I see no hands. No hands. Right, we call this internally the chicken leg. Why is it chicken leg? A chicken leg has 4 toes. You see here. This pattern also has 4 toes. The only thing we could think of was the wafer chuck. That's where the wafer sits on during the processing. But the wafer chuck has a distinct shape, but 3. It's a tripod which comes up to lift up the wafer on 3 pins. Anyone closer to the solution here? No, hands?
Vacuum pump? Deformation of the wafer.
No. Anyone else? Yes?
The spin that's behind the wafer when you.
A spring.
Yeah, there's a spring behind when you have a wafer.
Yeah, no, there's no spring, I'm afraid.
Oh, but when you have the indium phosphide or gallium arsenide, there always is a spring in the back.
Yeah,
when,
yeah.
When
No,
it looks.
yeah, it looks like it. It's a good one. I've not heard that one before. So that's great. Anyone else? No. Gas flow, that's a good one. We thought about that one as well.
2 problems, not 1.
No. It was one problem. Okay. So no chicken legs then for you. We started to imaging the Tsjerk a little different. Suddenly, out of the blue, I hope you can see it, a faint pattern here appearing. Yeah? So suddenly, okay, that starts to make sense. Then we asked the manufacturer of the equipment, and reluctantly they shared a drawing without any annotations to us of the Tsjerk. And in the HEST part, that is the so-called electrode, and then it's isolated in this particular shape, and the isolation had to wrap around that tripod shape, which is the lift pins. Anyone closer to the solution? Yes, electric field. Who said it? Good, so we're going to hire you. Indeed, it's the electric field, because these are electrodes and the clamping is working on the electrostatic force, clamping force for the wafer. That's not the whole story. Yes, I'm still okay. Or you hope for more. But obviously, all the test wafers and short loop wafers, they still had the same clamping mechanism where we didn't see it. But yeah, that's the issue we had here, and the configuration in the short loops. As we had, there was still always a little conductive layer left on the wafer, which then terminates the field lines. As from your high school, you probably know that. But if there's no conductive layer, in parts of the wafer, the E field pokes through it and sees also the surface of the wafer. So that was the problem. Yeah, we have that shape on the bottom. How does that appear and transpose on the top of the wafer? So, but that's more I can't say because that's confidential. So now I want almost my last slide. Two to go. So just to see what you think. So this issue you think was an unknown known. Maybe hands up. Who thinks it's an unknown known? No. Who thinks it's a black swan? I expected the whole room to think it's a black swan. Yeah. Okay. Yeah. We could not have predicted this. There's no way. In any case, we picked it up quickly. We solved this within 2 months or so. And by definition, if you solve an unknown problem, you always get a patent, because it's no one else had thought about that before, by definition. Also in this case, and you see this pretty recent. So this is all fresh example of how it happened and how to deal with it. Okay, interesting fact. When I was writing this presentation, I suddenly remembered that my experience with black swan went back to my youth. I grew up with with my grandpa's house. My grandpa was a park keeper in Sneek, which is a nice village in the north of the Netherlands. And we had a pair of black swans here. They're still there. But you also see that from the pictures here that around the pond of the black swans there's a fence, because the bad-tempered black swans you really want to keep at bay, and I learned that already when I was 7. And with that, the last slide, the takeaways of this talk, if you want to take anything home, is the serious investment in FMEA is essential. Also, the management at the business needs to express that. Use the FMEA to catch the known unknowns and the unknown knowns. And you have to be prepared for the unknown unknowns, which are the black swans. And how do you prepare for that? Build resilience, fail forward, and build flexibility in your schedule to go to different tracks. So into your team and into your planning to deal with the black swans. And with that, I'd like to thank you for your attention.
Well, I hope you can hear me. Yeah, all right, good. This was a very interesting lecture. Thank you. Unbelievable good. Tsjerk, a small present for you.
Thank you.
Some Q&A is possible, only we have limited time.
Yep.
So if there is somebody with a question, raise your hand. I have one person with a question for you.
How do you know when to stop looking for black swans? Because it's kind of an occupational hazard. If you have had a few of them, you keep looking for them maybe. How do you limit the resources, time to look for them?
That's a question of investment. So at some point the money runs out for the company. As you see, I was involved in startup companies, but they were relatively successful, as you saw, by acquisitions. And apart from the first one with AkzoNobel, are still in production and still alive. I've been told actually the photonic circuits I showed with the telecom boom, they're actually up in space at the moment, my design there. So so when to stop is really if the combination you need in design process development no longer stacks up to get actually a product to specification. That's the point to stop.
Thank you.